Hey, this is lecture 8, part 3. This is the example problem, match problem number 3. That's the only thing I'm going to cover in this part. It'll take a little bit of time. So let's get started. In this problem, so we'll give you a chance to read it. I'm going to read it with you. But a chicken farmer can buy a special food mix A at 20 cents per pound and a special food mix B at 40 cents per pound. Each pound of mix A contains 3,000 units of nutrient 1 and 1,000 units of nutrient 2. Each pound of mix B contains 4,000 units of nutrient 1 and 4,000 units of nutrient 2. If the minimum daily requirements for the chickens collectively are 36,000 units of nutrient 1 and 20,000 units of nutrient 2, how many pounds of each food mix should be used each day to minimize daily food costs while meeting or exceeding the minimum daily nutrient requirements? What is the minimum daily cost? Construct a mathematical model and solve using the geometric method. Okay, there's a lot of words here, so let's start breaking it down. If you think about it, we're talking about two different food mixes. Special food mix A and special food mix B. So that seems like that would be very likely to be our decision variables. I would say this is special food mix A would be X and special food mix B would be Y. We're also asked, what is the minimum daily cost? That sounds like a maximum minimum objective. So let's start doing this. I'm just going to do it right. I'm just setting it up real simple right now. So let's make this as X and this is Y. And then we're going to say our cost, we want to minimize. Our cost is equal to 0.2x plus 0.4y. Okay, and then after this, it looks like we need to start making a table. We have minimum daily nutrient requirements. So I think we're ready to start setting up our table, don't you? And I'm just going to go forward a little bit, and then I'm going to come back and actually set up the table. But if you want, right here there's some decision variables, a little table that you can use to get started, that sort of thing. Sometimes this is helpful, sometimes it's not. And make sure that you follow all the steps that you need. I'm going to do it without it, but I'll basically follow this format. So we're going to make decision variables. We're going to start with the decision variables X and Y. And X is special food mix A. X is mix A, and Y is mix B. And we've made our objective function, which is cost. Cost equals 0.2x, 0.2 meaning 20 cents, plus 0.4y. So let's start building up a little bit of a table to summarize our information. So we have X and Y. We have nutrients. If the minimum daily requirements for the nutrients collectively are 30 of this, okay, so minimum nutrient. And there's two different ones. So this is N1 and N2. So X has, each pound of mix A contains 3,000 of nutrient 1 and 1,000 of nutrient 2. And mix B, Y, contains 4,000 of each. And our minimum for nutrient 1 is 36,000. and for nutrient 2 is 20,000. Okay, so now we have our table. We also should note that x and y have to be greater than or equal to 0. We can't purchase negative food. Okay, now from here we should pay attention and go, yes, from this we can make some inequalities. And that would be our problem constraints. And it looks like for N1 it's 3,000. Mind if I'm just going to drop the 1,000 right now, and we can always add it back on. And we'll keep it on. 3,000 x plus 4,000 y equals 36,000, right? Oh, sorry, not equals. It needs to be, what is it? Less than or equal to. Yes? So it needs to be less than or equal to. And I don't know where my eraser is. There it is. It's hiding. Less than. No, it has to be minimum, so it's greater than or equal to. Greater than or equal to. And the same thing for nutrient 2. 1,000x plus 4,000 y has to be greater than or equal to 20,000. So we now have our constraints. So we want to graph this. So let's go ahead and graph. Like I say, I'm just going to multiply everything by 1,000. Just makes my life easier. We'll come back to it later. So we'll do x and y 0. So 36 divided by 4 is 9. And then we'll set a 0. 36 divided by 3 is 12. For this, 20 divided by 4 is 5, and 20 divided by 1 is 20. So we can graph this. We have graph paper available. Um, 20. Let's call this 20 right there. Five, 10, 15. Okay. So we have 0, 9, 5, 9, and 12. Let's start drawing some lines. We'll take a look at our constraints. We can do the test point 0, 0. And that would tell us that 0 is greater than or equal to 36, which is false. So we know that we're up above. That line didn't come in very dark, but that's okay. It's okay. You can see that. We'll switch colors. Here we have 0, 5, and 20. So we'll draw this line in. And we'll test 0, 0, which gives us 0 is greater than or equal to 20. This is false. This is false. So it's not. Pay attention to what our region is. We know that it'll have to be inside of this. So it'll have to be in the first quadrant. It can't be anyplace else. So we have a feasible zone, and that feasible zone is this whole section. That gives us some corner points. Let's identify what those corner points would be. So we've got a corner point here. We have a corner point here. This is not a corner point because it's not inside our feasible region, but this is a corner point. And this is a corner point. And this is a corner point. So let's figure out what those corner points are. So this one should be pretty straightforward. It's 0, 9. This one should be pretty straightforward. It's 20, 0. And this one we've got to calculate. And it is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. So 8, 3. Does that match up with what we have here? I believe it does. So now we have corner points, objective, and our objective function is c equals 0.2x plus 0.4y. Now remember, we have to multiply this by, when we're calculating from our corner points, we're going to have to multiply by 1,000 because that's what we did here. So it's just something to recall. So we have a corner point of 0, 9, a corner point of 8, 3, and a corner point of 20, 0. Let's calculate our objective values. I'm going to need my calculator for this. So this is 9 times 0.4. 9 times 0.4. I'm going to multiply it by 1,000. That equals 3,600. I'm going to do the last one. That's 20 times 0.2 times 1,000. Okay. Now remember, we want to minimize our cost. And the last one is 8. 8 3, so 0.2 times 8 is 1.6 plus 3 times 0.4 times 1,000 is equal to 2,800. If we're looking for a minimum, this is our minimum. And remember, multiplying by 1,000. So we have a minimum at x equals 8,000, y equals 3,000, and then c equals I do this right? Okay. So then C equals 2,800 is the minimum. Okay. And this would be pounds and pounds to meet our minimum daily requirements. And just to verify, there we go. There is, however, no maximum function. Okay. And there we go. We're wrapping this up. That's the end of lecture 8.